Okay, I want to talk about two important properties of the determinant right now. They're both very useful, very deep. And the first is that if you have a product of matrices, so remember when we were talking about determinants, we're always talking about square matrices. So here, if I have A times B, they're both the same dimension. They're both, say, n by n. And there's this beautiful fact that the determinant of A times B is the determinant of A times the determinant of B. We say that the determinant is multiplicative. Sort of it respects multiplication or preserves multiplication, maybe is a better way to say it. So like, and this is useful because somehow we're reducing, a determinant almost reduces a matrix to a number. And then the question is, what does that number tell us? And we already know some things it tells us, but in particular, the fact that it respects multiplication means if we can sort of, if we have a product of matrices, we can still understand the determinant of the product and what that number tells us. Okay, so that's the first property, which I'll justify in a moment. And then the second property is that A is invertible. You can actually tell if a matrix is invertible if and only if the determinant is non-zero. And so that's also big because that's another, this is actually another reason why reducing a matrix to a number is still useful because, you know, you can take some 50 by 50 matrix and you want to know if it's invertible and you could just ask for its determinant, although that's kind of hard to compute, but at least it's just a number. And then you just have to see if that number is zero or not. And if that number is not zero, then it is, then the matrix is invertible. So, and as an auxiliary point here, it turns out that this actually follows from 1 and 2 very quickly, or actually just follows from 1 very quickly, that the determinant of A inverse, if it is not 0, so if A is invertible, then it's 1 over the determinant of A. If, you know, if A is invertible. Which, by the way, you could write, if you just want to be a little goofy about it, we could write as the determinant of A inverse, so you're just moving the minus sign sort of outside, you know, some parentheses or something. Right, so that is the, that will follow very quickly from number 1. So let's talk about number 1. So why are these true? And number 1, I mean, from the formulas that we have for the determinant, it's sort of like not at all obvious that the determinant would be multiplicative. But if we interpret it from the transformation perspective, which was our original sort of definition of the determinant, then it actually becomes natural. So if we think about it right, remember that A is the matrix of some transformation, let's call it T sub A, and B is the matrix of some transformation T sub B. And these are both from, let's just say these are n by n matrices. These are both from Rn to Rn. These are maps, linear transformations from n-dimensional space to itself. And the whole point is that it comes from, you know, the matrix gives a transformation is given by a matrix, and T sub B of X is B times X. And so if you just think that the whole point of the determinant of A is this sort of, we said like the volume scaling factor, right? It's T sub A scales volumes by the determinant of A. So I'd really rather say it's for this transformation T sub A. I mean, that's really what the determinant is. And same thing for T sub B, right? I mean, I could put a B here and it doesn't affect anything. And so now if we think about A times B, well, A times B is the matrix for, we actually use this to define matrix multiplication. AB is the matrix for the composition T sub A composed with T sub B. right? You know, here I mean that like T sub A composed with T sub B of X by definition is T sub A of T sub B of X. And we saw how this is really just gives you A times Bx, right? Because replacing T sub A and T sub B with the matrices A and B. Okay, so, but if you, so what does that mean? I mean, if we take some object and we hit it with T sub B, so T sub B scales objects by determinant of B. I mean, it sort of, this becomes sort of clear at this point, right? Scales objects by T sub B, oops, sorry, by the determinant of B. T sub A scales objects by the determinant of A. Well, T sub A composed with T sub B scales objects by the determinant of A times B. But just imagine what happens here if you apply T sub B and then you apply T sub A, right? So if I have some, you know, just say we're in Rn, that's supposed to be an N, and I have some object, you know, some object with area, let's just call this object S, like a set. And then the, you know, so then if we apply our transformation, T sub B, that's the one we're applying first, then our object is now, you know, I mean, it can't be so different in shape, but it's maybe been rotated and scaled or something. And so this is T sub B of S. And this has area, we have to make some more room here. This has area, yeah, so if this has area of S is that area, let's just call that, I don't want to use A, or let's just call that little s. It's supposed to be a big S and a little s. And then what's the area of this? Well, the area of this is the determinant of B times little s, right? And then if we now apply T sub A, then we get some new, I'm not sure why we're still in the first quadrant, it could be anywhere, but you know, maybe this is like over here now, some blob. Then this is T sub A of T sub B of S. And the area is the determinant of A. It's been scaled by now the determinant of A times the determinant of B times S, whatever that little area was. And okay, but on the other hand, if we apply, if we just think about doing the transformation directly, you know, doing T sub A following T sub B, composed with T sub B, then that actually says that the area is scaled by we know that A times B is the matrix for T sub A composed with T sub B. So that scales the area of S by determinant of AB. And so really what we've just shown is these are the same scaling factor. Therefore, the determinant of AB equals the determinant of A times the determinant of B. So on one hand, you're considering two steps where you're just scaling by determinant of B, then scaling by determinant of A. The other one you're thinking of this is one step where you just scale by the determinant of AB. You get the same answer, therefore those are the same. And that's amazing because again, it's like, there's no formulas, there's no anything, it just follows from the sort of notion. And so that's another reason why the area notion, or the area scaling factor, volume scaling factor notion is really the right way to think about determinants. Okay, second, to show that the determinant of A inverse, well, that A is invertible if and only if determinant of A is 0. Well, let's actually go this way first, proving this direction. So assuming that A is invertible, that means A inverse exists, right? And then what we know is that A times A inverse is the identity matrix, the n by n identity matrix, right? And then if we just take determinant of both sides, then on the right, we get the determinant of the identity. That's just ones along the diagonal. So we just multiply those and you get 1, right? But then if we use property 1, which we just showed the fact that the determinant is multiplicative, we get the determinant of A times the determinant of A inverse is 1, and immediately that shows the determinant of A inverse is 1 over the determinant of A. Determinant of A inverse is 1 over the determinant of A. And that means the determinant of A better not be 0, because you can't divide by 0. Okay, so that's kind of that's well, first that also gives the formula that I mentioned above also, that, this formula, that's if A is invertible, that's the determinant of A inverse. Second, yeah, it's something that follows very nicely from this sort of multiplicative property. If I want to prove the backwards direction, if I want to say that if the determinant of A is not 0, then A is invertible. Well, there's a way to do this also. It's slightly more, you have to think about, I'm not sure I can give it just directly. Knowing the determinant of A is not 0 doesn't necessarily mean A inverse exists, right? I mean, if it exists, you get this formula I just drew in boxed in orange, but it doesn't guarantee that inverse exists by itself. So I think the best way to think of it is the following. Say A row reduces to echelon form, let's call that matrix U. Then we know from the last video from how row reduction affects determinants that this is some constant, let's just say K, times the determinant of U. Determinant of A is some constant times the determinant of U, where the constant came from swapping and scaling rows, right? It's the only way that we can affect the determinant. And in particular, that's a non-zero constant because we've only scaled rows by swapping just changes the sign, so that's scaling by -1. And scaling a row, we don't want to scale a row by 0. That would just make the whole row 0. So we know K is not 0. And so really the determinant of A is 0 if and only if the determinant of U is 0. But the determinant of U is the product of the diagonal elements, right? So determinant of U is sort of, if we think about writing the diagonal elements as, U sub 1, 1 is the top left. And these are and so that's, if this is not 0, that would imply none of these numbers are 0. U2, 2 is not 0, etc. And that means that there's a pivot. The pivots are all where they're supposed to be, right? Because if it was not invertible, you would row reduce. You'd get somewhere where you'd get a free variable column. You wouldn't just move over 1 and down 1 to get the next pivot. And so that means that U has n pivots. But we exactly know that that means, let me just start here with 0 not equal to determinant of A, just to make sure we're on the same page here. So that means, so okay, that just did that at the top up here. And we've shown that U has n pivots, which implies that A is invertible. You can actually use this to give the argument in both directions. If A is invertible, then U better not, then U will have n pivots, so these are all sort of reversible arrows. But I wanted to give the argument above just because I like it's the most natural interpretation. Okay. All right, so that justifies both of those. Great, and so let me just go back to the top here because these are nice statements that are worth displaying again. Right, the determinant of, yeah, this is beautiful, and this is beautiful, and this is a nice formula, and I'll stop there.